This is EE300 Linear Circuit Analysis 2, Module 3, Video 1, the Sinusoidal Steady State. In this video, we'll take a status check of where we are. We'll review the concept of exponential inputs to a linear circuit and what happens to the output. We'll introduce the sinusoidal steady state, and then we'll have a summary and some previews. So let's see where we are on these things. We've already had the Laplace transform. We learned how to use it with differential equations, and also we introduced the S-domain circuit models. And from that, we can get the total response of the circuit to arbitrary inputs as long as they had a Laplace transform. And in the second module, we introduced the idea of zero-state response network functions, and that lets us talk about the input-output behavior either at one port where we've had the current and voltage related by either an admittance or a driving point admittance or a driving point impedance, or from one port to another where we usually use the voltage-to-voltage transfer function. We also learned how to design circuits to implement a particular network function. In this model, we're going to introduce the frequency response concept. To start there, today we'll do the sinusoidal steady state, and then in the future videos, we'll look at the frequency response of first-order circuits and second-order circuits, and then we'll look at how poles and zeros determine the frequency response. Then we'll go to what's called Bode's method for plotting the frequency response, which has the great power that it lets us look at a frequency response plot. And these are going to be graphic plots of frequency response magnitude and frequency response angle versus frequency. But Bode's method lets us identify where the poles and zeros are by the way the frequency response changes. And then we'll look at the relationship between frequency response and step response, which gives us some implications when we choose alternatives among different designs. So let's review the exponential input idea. We saw that when we had a circuit that had a voltage-to-voltage transfer function, V2 of S over V1 of S, that if the input was an exponential with rate S0, and these are multiplied by U of t, so they're zero-state response inputs, then the output was H of S0 e to the S0 t, an exponential of the same rate with a new amplitude, and that could be a complex rate and a complex amplitude, and then the natural frequency returns, where those correspond to the poles of the network function. That would be the rates of this exponentials in the natural frequency terms. And again, since it was a step input, it's got a U of t on the output. So when all the circuit poles are in the left half plane, that natural response term is all those are going to go to zero as t gets bigger. It doesn't have to go all the way to infinity; it just has to get big enough that they decay away. And if that's the case, and if the S0 is on the j-axis, if it's on the imaginary axis in the S-plane, now we're talking about either the step, unit step, where the rate is 0, or sinusoids with rates j omega naught, or j omega something, then the only thing that's going to be left is h of S0 e to the S0 t. But that's going to keep going. For those kind of inputs, that's going to go forever and ever. So that's a steady state response. It's either a constant response for the step or a steady state response for the sinusoids. Let's look at an example with the step. Here's the RC circuit with the output across a capacitor. Here's some familiar parameters. We know the network function here, 1 over RC over S plus 1 over RC. We've done it a bunch of times, and we'll plug those in, we get 1,000 over S plus 1,000. So when the input is a unit step, we think of that as an exponential with a rate 0. Because e to the 0t is 1. So in this, you can think of 1 as an exponential with a rate 0, an argument 0. And so in that case, the output is going to be h of 0 times e to the 0t, and then the natural frequency, the natural response term, k e to the minus 1,000t. And after the e to the minus 1,000t decays away, after 5 milliseconds, all you have to wait, the output is v2 of t equals h0. It's just since you had a unit input, then the gain h0 is called the h of 0. Is called the DC gain, and so the output is just h of 0 times 1, the input amplitude. Well, let's see how this plays out with sinusoids. Let's do the same circuit, but let the input be cosine 1,000t u of t. And in order to exploit the exponential property, we have to see the cosine as a superposition of an exponential with a rate j 1,000 and an exponential with a rate minus j 1,000. And you add those together, and that would give you twice a cosine, so you have to take a half there. And then it's still times u of t. It turns on at t equals 0. So when we apply this to the circuit as the input, we're going to get e to the j 1000t is going to evoke h of j 1000 e to the j 1000t, and e to the minus j 1000t is going to evoke h of minus j 1000 times e to the minus j 1000t. And then we still have the natural response term, e to the minus 1000t, with some scale factor we're not bothering to calculate. So we take h of s and plug in s equals j 1000. And when that's the case, you get 1000 over j 1000 plus 1000. The thousands all cancel out. You get 1 over 1 plus j. And you can, in this case, we'll multiply by 1 minus j over 1 minus j to get 1 minus j over 2. And then we'll realize that 1 minus j is a complex number in the fourth quadrant of the complex plane with a real part 1 and an imaginary part minus 1. So thinking of it as a vector, it's got a length root 2, and it makes an angle of 45 degrees with the positive real axis. So we write that as e to the minus j pi over 4. So we can identify that first term, root 2 over 2, is the magnitude of h of j 1000. And we can identify minus pi over 4 as the angle of h of j 1000. Now we also need h of minus j 1000. So look at that. That just turns out to be the conjugate of h of j 1000. So it's going to be root 2 over 2 e to the plus j pi over 4, because to get the conjugate from a complex number, you just replace every instance of something j with minus something j. And so it's got the same magnitude, but the angle is the negative of what the h of j 1000 was. And this is always going to be the case, that when you evaluate h of s at j some frequency, if you evaluated at h of minus j that frequency, you're going to get the conjugate of what you had before. Because the differential equations we're dealing with have real coefficients, and we know that those coefficients turn into the coefficients of the numerator and denominator polynomial in the rational function that makes up h of s, with the input side going to the numerator and the output side going to the denominator. And if you think about a powers of s, then even powers of s, when you plug in s equals j omega, you still get real numbers about for all real even powers. And for odd powers of s, when you plug in h of j omega and h of minus j omega, you get the conjugate. You get h, if it's a plus j, if you have j omega to the first power, and minus j omega to the first power, you get minus j omega. So it's always going to be the case that h of minus j omega is the conjugate of h of j omega. So let's plug these in here now. We've got values for h of j omega, h of j 1000, and h of minus j 1000. So we plug them in. There's a missing t in that first equation there. I'm sorry I didn't catch that one. So h of j 1000 is root 2 over 2 e to the minus j pi over 4. H of minus j 1000 is a conjugate of that, root 2 over 2 e to the plus j pi over 4. And then we're going to look at the e to the j stuff. And you got e to the j 1000t minus pi over 4 on the left, and e to the minus j 1000t quantity minus pi over 4 on the right. And so that's something plus its conjugate, which is twice the real part. And twice the real part of e to the jx is cosine, is cosine of x. Excuse me, half the real part. The something plus its conjugate is twice the real part of the something. The something in this case is e to the jx. And so the real part of that is cosine of x. And so when we can write this, the twice part kills off the half out front, and we get root 2 over 2 cosine of 1000t minus the angle, which is 45 degrees. And again, the way I do this is if I'm writing in terms of exponentials, I write my angles in radian notation. And if I'm writing in terms of the argument to cosine or sine, I write my angles in degree notation. I'm not sure if that's a standard or not. It's just the way I do it. So after the natural response decays away, the k e to the minus 1000t, we're just left with root 2 over 2 cosine 1000t minus 45 degrees. And we can see that that's the magnitude of h of j 1000. And then the cosine is still frequency 1000. And so you get cosine 1000t plus angle of h of j 1000, which was minus 45 degrees. And that's going to be our general form. So this derivation we've done here, and what we're going to do for the more general case, is not how you solve these problems. You don't want to go through and do this every time. We're doing this to derive the principle and to show what the principle is. But then we'll have a couple of examples here that just show you how you apply it. It's pretty simple. You plug in j omega for s. So here's the more general case. We've got a sinusoid. It's got an input omega sub a, an amplitude v sub a, and a phase phi sub a. So we can write that as v sub a cos omega sub at plus v sub a. And we write that in terms of complex exponentials as 1/2 v sub a e to the plus j omega sub at plus v sub a plus va e to the minus j quantity omega sub at plus v sub a. And then I pull out the e to the j phi terms because those aren't time varying. I'm interested in the complex exponential stuff had to do with the time varying. That's just an amplitude. So that va e to the j phi sub a, that's your good old complex amplitude you may recall from when you did phasors. And then we have the other term over there, which is the complex conjugate of that, va e to the minus j phi sub a, and the frequency there is e to the minus, the cos of the exponential is e to the minus j omega sub at. So when we get the output, we have 1/2 the scale factor va e to the j phi sub a and h of j omega sub a times e to the j omega sub at. And then the right-hand term, which went with the negative frequency minus j omega sub a, we have v sub a e to the minus j phi sub a, h of minus j omega sub a, and then the e to the minus j omega sub at. You have your natural response term. It didn't turn on until t equals 0, so it's still got a u of t out there times everything. Now we use the fact that h of minus j omega is h conjugate of j omega. So the right-hand term, all we've done is replace h of minus j omega sub a with h conjugate of j omega sub a. Natural response still carrying on, u of t carrying on. Here, now we've written h of j omega sub a in terms of its magnitude and angle. So we get magnitude h of j omega sub a, e to the j angle h of j omega a, and then in the conjugate we get magnitude, the same magnitude, h of j omega sub a, and then e to the minus j omega sub a. It's still got the natural response, and yes, there's a u of t that just fell off the side there because the slide wasn't wide enough. And when we put this all back together, the term on the left plus the term on the right is something plus its conjugate, so we get twice the cosine again, and the twice kills off the half. So we get magnitude h of j omega sub a times va, the original amplitude, cosine omega sub at plus phi a, the original phase, now with an added angle plus angle h of j omega sub a, and then the natural response term and the u of t. And as usual, when the natural response goes away, you're just left with the cosine, and that's why that's called the sinusoidal steady state. The sinusoidal steady state is the magnitude times the original amplitude times cosine of the same frequency with the original phase, but with the additional phase, angle h of j omega sub a. One more time. If the input, here, let's take it to the further. What if we turn, if we wait long enough, what's the difference between turning on the input previously, right? Instead of waiting for all the exponentials in the natural response to go away, let's turn it on long enough ago that they've all gone away by the time we start looking at stuff. So now the input is a cosine that's been going forever. Meaning we turned it on so far ago that we don't see any transients. And the output is just that sinusoidal steady state term. We put in an everlasting cosine, we get out an everlasting cosine, the same frequency. We put in a cosine omega a, we get out cosine omega a. We put in cosine omega at, we get out cosine omega at. If we have an input amplitude VA, we have an output amplitude magnitude h of j omega a VA. And if we had an input phase phi a, we have an output phase phi a plus angle j of omega a. That's the sinusoidal steady state. It's like Ohm's law for signal processing. You know that V equals R times I. You know that when you put a cosine of a frequency omega a in, you get out a sinusoid of the same frequency, the cosine of the same frequency. And the amplitude is scaled by the magnitude of h of j omega a, and the angle is increased by angle of h of j omega a. I say increase, meaning you add it to it. The angle may be negative, which is actually decreasing it, but we assume if it's positive, what we mean there is if it's positive, it's increased. Let's do another example. Here's the series RLC circuit with the output across the capacitor. We know the transfer function here is 1 over LC over S squared plus R over LS plus 1 over LC. If you don't know it, you ought to be able to derive it in about 10 seconds. We plug in the numbers, so we get 10 to the 6 over S squared plus 10S plus 10 to the 6. And now let's plug in cosine 1000t, but with an amplitude of 0.1. So what comes out? You evaluate H at the frequency S equals J 1000. So we get 10 to the 6 over J 1000 squared plus 10 times J 1000 plus 10 to the 6. And J 1000 squared is minus 10 to the 6, so those kill each other off. And so you get 10 to the 6 over 10 to the fourth and scale factor, and you have that j there in the denominator. So you get 100 over j. And since 1 over j is the same thing as minus j, you get minus j at the 100. And then you can realize that minus j is a complex number with a magnitude 1 and an angle of minus 90 degrees. So we write that as 100 e to the minus j pi over 2. So V2 of t is 100, the magnitude of h of j 1,000, times 0.1, the original input amplitude, cosine 1,000t minus 90 degrees, the angle of h of j 1,000. And we can simplify that. 100 times 0.1 is 10, and cosine minus 90 degrees is a sine, so that's 10 sine 1,000 t volts. You put in a cosine of amplitude 0.1, you get out a sine, the same frequency of an amplitude 10. Let's do still one more example. Here's the RC circuit with the output across the resistor this time. Same familiar parameters. So in this case, the output is S over, the transfer function is S over S plus 1 over RC, which is S over S plus 1,000. Now let's put in 10 cosine 1,000t for this one. So again, we evaluate h of j 1,000, j 1,000 over j 1,000 plus 1,000. That's j over 1 plus j. J is a complex number, e to the j pi over 2. 1 plus j is a complex number, root 2, e to the j pi over 4. So 1 over root 2 is the same thing as root 2 over 2, and pi over 2 minus pi over 4 is pi over 4. So h of j 1,000 has a magnitude of root 2 over 2, and it has an angle of 45 degrees. So V2 of t is root 2 over 2, that's magnitude of h of j 1,000 times 10, the input amplitude times cosine 1,000t, and now we've increased the angle by 45 degrees. And we can write that as 0.707 cosine 1,000t plus 45 degrees. And that's volts, of course. If the input was volts, the output's volts. And that's how you do the sinusoidal steady state. You evaluate h of s at the input frequency j 1,000. You find the magnitude and the angle of h of j 1,000, or h of j of whatever frequency you're interested in. And then you write the output as magnitude h of j 1,000, input amplitude, cosine, input frequency t, plus angle h of j, whatever. So to summarize, when you have a linear circuit whose input is amplitude VA, frequency omega sub A, phase angle phi sub A, the output is going to be magnitude h of j omega sub A times v sub A, same frequency omega sub A t, same frequency omega sub A, and then the phase is increased from phi A to phi A plus angle h of j omega sub A. The response of a linear circuit to a sinusoid of frequency omega A is a sinusoid of the same frequency, where the amplitude has been scaled by magnitude h of j omega sub A, and the angle has had angle h of j omega sub A added to it. Think about this for a second. The fact that we have linear circuits means we put in a sinusoid of one frequency, we get out a sinusoid of the same frequency. If the frequency changed every time we input a sine, I mean our voices, music, images can be represented as superpositions of sinusoids. You'll learn more about this in CEC 315 if you haven't taken it yet. So through Fourier analysis, you can build waveforms out of superpositions of sinusoids. When you put those through a linear circuit, if it changed the frequency, everything would be a mess. You say hello, and the cat would come, meow. The frequency would change. Something would happen, and that wouldn't be good. Instead, we just changes the amplitudes and the phase angles, and that means it's still perceptible. So next videos, we'll talk about the frequency response, plotting the magnitude and the angle of h of j omega versus omega. That's how we'll learn to think about these things. Instead of doing them one frequency at a time, we'll usually do them over all frequencies, and we'll understand what they do for different regimes, low frequencies, middle frequencies, high frequencies. We'll do first order circuits, and we'll do second order circuits, and then we'll get into talking about how poles and zeros influence the shape of the frequency response. So this has been EE300 Linear Circuit Analysis 2, Module 3, Video 1, the Sinusoidal Steady State.